So we've just managed to count to 6. That means that to count to 7, we need to add one more in the ones place. And now that all of them are now 1 again, we're out of symbols and we have to add another placeholder, a place value. This one's going to be 2 to the 3rd power. We've got 0, 1, 2, 2 to the 3. 2 to the 3rd power is 8. And all these are going to switch back to 0. Since 2 to the 2 is 4. 2 to the 1 is 2. 2 to the 0 is 1. 4 plus 2 plus 1 is 7. And this one's 8. So this makes sense that 1 to the 3rd. So 1 in the 8th place is 8. Plus 0 plus 0 plus 0 is going to be 8. So 7 and then 8. So that makes sense. So it doesn't look familiar. And we're adding places at a way rapider pace because we only have 2 digits here. But we're still, it's still the same values that we're used to in a decimal system. So converting between the two is actually pretty simple. So again, we did 0, 1. Then 1, 0 for 2. 1, 1 for 3, because 2 plus 1 is 3. And then 1, 0, 0 for 4. 1 in the 4th place, 0 in the other places. 1, 0, 1. 4 plus 1 is 5. 1, 1, 0. 4 plus 2 is 6. 1, 1, 1. 4 plus 2 plus 1 is 7. And then 1, 0, 0, 0 is 8. 8 plus 0 plus 0 plus 0 is 8. Okay. And then one more in the ones place. 8 plus 1 is 9. Change this one back to 0. Put a 1 here. We've got 8 plus 2 is 10. Put another 1 in the ones place. 8 plus 2 plus 1 is 11. Put a 1 here. And 0's here. 8 plus 4 is 12. And put another 1 in the ones place. 8 plus 4 plus 1 is lucky 13. So that's how we count in binary. That's how place value gets added in binary. So when you see a longer binary number like this, to figure out what it is in decimal, all we have to do is break it out. And from this end, from the right side, we go 1, 2, and you can do this if it helps, 2 to the 0, 2 to the 1, 2 to the 2, and then figure out what those things are. But it's also kind of easy to just remember that 2 to the next power is just this times 2. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and so on and so forth. So that's what I did right here. I took this number and I broke it out and said 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. And then I look at the ones that have 1s. The ones that have 0s don't matter because it's this times 0. And 64 times 0 is nothing. 32 times 0 is nothing. So I don't care about those because they don't matter. They're 0. So I add up the ones that have 1s. And it's 1 times 28. 1 times 16. 1 times 8. 1 times 4. 1 times 1. Okay? So it's just 28 plus 16 plus 8 plus 4 plus 1 equals 157. That's how I figure out what this binary number is in decimal. It's pretty simple. Okay. So why does this matter? Why do we need to know what this number is in decimal? Why did we need to figure this out? Why did the binary number system become a thing when we already had the decimal number system, which makes way more sense and we're already familiar with it? Well, let's talk about it. Part 2, signals. Think about this for a minute. How many combinations can you make from these 26 signals? These 26 symbols. If you needed to communicate a message to me using these 26 symbols, how many messages could you send me? Pause if you need to think about it. You could send me quite a few. You could send me, hey, Miss Neighbors. You could send me the entire text of Great Expectations. You could send me whatever, because these are the letters that we use to communicate. That's great. However, it turns out that we didn't have these 26 symbols with which to communicate to our machines. How many symbols could you make from this system? Pause if you need to think about it. Turns out this system, it can be on and off. It can have a current running through it, and it can not. So there's basically 2 symbols, 2 signals. Okay? So we had to figure out how to create some way of communication using only 2 signals. Well, it turns out we were pretty good at that. So if you think back to our ifs and our elses and all of our Boolean stuff, we actually figured out how to build logic gates. So we figured out how to represent and, or, and not, as well as some more sophisticated versions of those in circuits. And I don't just mean on paper, I mean these right here are actual, these are diodes, these are resistors, here are a couple of buttons, there's a power source that you could connect or disconnected over here, there's some lights. So if you pressed both of these buttons, the light will come on, and this light will not come on unless both of these buttons are pressed, because this represents an and, or this is an and, what they call a gate. And this is an OR gate. So this light will come on if either of the buttons or both of the buttons are pressed, because it's an OR. So you know and you know OR, and this is and OR represented in a circuit. So they figured out how to do that with an electric circuit. This is the logic that you've been learning in hardware version. And they figured out how to make this so sophisticated that they put all of these different ones together to make something where the signal, the on or the off, the true or the false, the 1 or the 0 would stay. And we're going to talk about that in the next video.